In the winter of 1896, in a laboratory in Paris, a French physicist wrapped a photographic plate in thick black paper and placed it in a desk drawer beneath a uranium compound. He was testing whether fluorescent minerals could expose photographic film through the paper when stimulated by sunlight, a project related to the recent discovery of X-rays by Wilhelm Röntgen. But the Paris sky was overcast for days. The experiment could not proceed. He put the uranium compound and the wrapped photographic plate in the drawer and waited for the sun. When he developed the film several days later, expecting to find nothing because no sunlight had activated the uranium to fluoresce, he found a vivid, sharp image. The uranium compound had exposed the photographic plate through the black paper without any sunlight, without any external activation, without any energy source that physics could account for in 1896. The uranium was spontaneously emitting something invisible. Something that passed through solid objects. Something that had no known source of energy. The physicist was Henri Becquerel. The phenomenon he had discovered was radioactivity. And what it meant, what the invisible emissions from uranium revealed about the structure of matter and the nature of energy, would not be fully understood for decades, would require the greatest scientific minds of the early 20th century to decode, and would transform human civilization in ways that were simultaneously the most beneficial and the most terrifying in the history of science. The story of radioactivity's discovery begins with Becquerel's drawer in 1896. But the full story, of the two brilliant Polish-French women who would spend their careers illuminating what Becquerel had found, of the New Zealand-born physicist who would decode the nature of radioactive emissions, of the Italian-American physicist who would split the atom, of the two scientists who would transform theoretical nuclear physics into the most destructive weapon ever built, is one of the most extraordinary intellectual and human dramas in the history of science. Before Becquerel and before uranium and before the specific accident of a cloudy Paris winter that made the photographic plate unnecessary, there was the broader context of 19th century physics, the specific intellectual landscape of a science that had, by the 1890s, achieved what seemed to many of its practitioners to be a near-complete description of the physical world. Classical physics at the end of the 19th century was an edifice of extraordinary achievement and apparent completeness. Newton's mechanics described the motion of objects from falling apples to planetary orbits. Maxwell's electromagnetic theory described light and electricity and magnetism in a single unified mathematical framework. Thermodynamics provided the laws governing heat and energy. The periodic table organized all known matter into a systematic scheme. Chemistry had established the atomic theory of matter, that all substances were composed of atoms that combined according to specific valence rules to form molecules. The specific consensus of the leading physicists of the 1890s was that the major problems of physics had been solved and that the future of the discipline lay in refining the precision of existing measurements rather than discovering new principles. Lord Kelvin, the most distinguished British physicist of the era, whose contributions to thermodynamics and electromagnetic theory had been foundational, famously expressed this view, suggesting that there were only two small clouds on the horizon of classical physics. Those two small clouds, the failure of the Michelson-Morley experiment to detect the ether and the specific problem of black-body radiation, would eventually produce special relativity and quantum mechanics. The discovery of radioactivity was the third cloud that Kelvin had not yet seen. Wilhelm Conrad Röntgen made the discovery that immediately preceded and directly enabled Becquerel's. On November 8, 1895, in his laboratory at the University of Würzburg, Röntgen was experimenting with cathode ray tubes when he noticed that a fluorescent screen on the other side of his laboratory was glowing even though it was far from the tube and the tube was covered in cardboard. The cathode rays themselves could not have reached the screen, they were absorbed by short distances in air. Something else was coming from the tube. Something new. Röntgen spent 6 weeks investigating the new rays in near-total secrecy before publishing his results in December 1895. He called them X-rays, the mathematical symbol for the unknown. The announcement created the immediate sensation that genuinely revolutionary scientific discoveries occasionally produce. Within weeks, X-ray photographs were being taken in hospitals around the world, revealing the internal structure of living human bodies for the first time in history. Within months, the discovery had been replicated in every major physics laboratory in Europe. Within a year, it had transformed medical diagnosis permanently. It was Röntgen's discovery that prompted Becquerel's. The question of whether fluorescent minerals that glow when exposed to light, might also emit X-rays was a natural one for a physicist whose father and grandfather had both studied fluorescent materials and whose family's collection of uranium compounds sat in his laboratory cabinet. The investigation that produced the famous photographic plate in the drawer was motivated by Röntgen's discovery and led by the specific logic of a physicist asking whether fluorescence and X-ray emission might be related. They were not. The exposed photographic plate in Becquerel's drawer revealed something far stranger than a fluorescent version of Röntgen's X-rays. The uranium compound had exposed the plate without fluorescence, without external energy input, apparently spontaneously and continuously. The emission appeared to come from the uranium itself, from the very substance of the matter rather than from any activation by external energy. Becquerel published his discovery in February 1896. He continued to investigate the phenomenon, demonstrating that the emissions were specifically associated with uranium, that they were continuous and apparently inexhaustible, that they could ionize air, that they were not affected by temperature, pressure, chemical state, or any physical or chemical change he could induce in the uranium. The uranium was doing something that classical physics had no category for. He had discovered radioactivity. He had not named it. He had not understood it. He had not even found it particularly interesting. His subsequent career suggests a man who recognized the importance of his discovery intellectually, but who found the subsequent investigation less compelling than the fluorescent studies he had originally intended to pursue. The systematic investigation of what Becquerel had found was conducted by others. The most important of those others was Marie Curie. Marie Sklodowska was born on November 7, 1867, in Warsaw, then under Russian imperial rule as part of the partition of Poland that had erased the Polish state from the map of Europe. Her childhood was formed by the specific combination of intellectual richness and political oppression of a Polish intelligentsia family under Russian occupation. Her father was a physics teacher, her mother the principal of a Warsaw girls' school, both committed to education as the specific form of resistance available to a conquered people. She was exceptional in mathematics and physics from her earliest education, and found, in the specific world of late 19th century Europe, that being exceptional in mathematics and physics was not sufficient if you were a woman and if you were Polish. The University of Warsaw did not admit women. The universities of Russia did not admit women. The specific educational apparatus of the Russian imperial system was designed to keep Polish intellectual culture subordinate. Teaching in Polish was banned, teaching Russian patriotism was compulsory. She participated in the Flying University, the clandestine educational network that Polish intellectuals maintained in defiance of Russian prohibition, holding secret classes in private homes, rotating locations to avoid detection, providing to Polish women the higher education that the official system denied them. It was a specific act of intellectual resistance that shaped her understanding of what education was for and what it cost. She came to Paris in 1891, to the Sorbonne, which admitted women to its science programs when no institution in Poland would, and proceeded to distinguish herself in physics and mathematics with the specific combination of extraordinary ability and extraordinary work ethic of someone who has had to fight for every educational opportunity and intends to make full use of the ones finally available. She met Pierre Curie, the French physicist whose work on piezoelectricity and crystal symmetry had already established him as one of the most original experimentalists of his generation, in 1894, and their partnership became both a scientific collaboration and a marriage that was, by the evidence of their letters and the testimony of their colleagues, one of the most genuinely equal and genuinely devoted scientific partnerships in the history of science. She chose radioactivity as the subject for her doctoral thesis, the first woman in France to pursue a doctoral degree in physics, in 1897. The specific reasons for her choice are worth noting. Radioactivity was new. Nobody had systematically investigated it. The field was open in a way that established fields were not. A woman entering an established field of physics in the 1890s would encounter the accumulated institutional advantages of the men who had worked in it for decades. In radioactivity, the field was so new that those accumulated advantages did not yet exist. She borrowed Pierre's electrometer, the precise electrical instrument he had designed and built for his own research, and used it to measure the ionizing effect of uranium radiation on the air surrounding uranium compounds, producing quantitative measurements of radioactive intensity with a precision that Becquerel's photographic plate method could not match. The electrometer allowed her to measure, for the first time, the specific quantity of ionizing radiation produced by a given amount of uranium compound, and to compare different compounds systematically. She made her first major discovery almost immediately. The intensity of the radiation was proportional to the amount of uranium in the compound, regardless of what the other components of the compound were. The radiation was a property of the uranium atom itself, not of any chemical compound it formed, not of any molecular interaction, but of the atom. This was a profound departure from everything that classical chemistry and classical physics understood about the behavior of matter. In the classical framework, the properties of a substance were determined by its chemical state, by the specific molecules and compounds it formed. Marie Curie was demonstrating that radioactivity was an atomic property that transcended chemistry entirely. She also tested thorium compounds, another element that had been suggested as possibly radioactive, and found that thorium was indeed radioactive, coining the word radioactivity in the specific paper where she reported this finding. The word was hers. The concept that radioactivity was an atomic property was hers. The systematic measurement approach that made all subsequent quantitative radioactivity research possible was hers. The second major discovery followed from the first. Working with uranium or rather than pure uranium compounds, she found that some uranium ores were significantly more radioactive than pure uranium itself, implying that they contained an unknown element, or elements, even more radioactive than uranium. The specific logical reasoning was elegant and clear. If radioactivity is an atomic property, and if this ore is more radioactive than the uranium it contains, there must be another radioactive element present. Pierre set aside his own research to join the search. The search required processing enormous quantities of uranium ore, the mineral pitchblende, mined in Bohemia, the most radioactive ore known, to concentrate and identify the unknown radioactive element or elements. The work was conducted in a converted shed behind the School of Physics that their colleagues described as resembling a cross between a stable and a potato cellar, with a leaking roof, an earthen floor, and no adequate ventilation for the chemical processing that was required. In July 1898 they announced the discovery of the first unknown radioactive element, naming it polonium after Marie's occupied homeland, the specific patriotic gesture of a Polish scientist who could not return to her country. In December 1898 they announced the discovery of the second, radium, from the Latin word for ray, a name that reflected the extraordinary radioactivity of an element that glowed blue-white in the dark from its own radiation. They had identified two new elements from nothing but the excess radioactivity of pitchblende. But identification by radioactivity measurement was not the same as chemical isolation. To convince the skeptical scientific community, they needed to produce measurable quantities of pure radium and polonium for chemical characterization. The isolation of radium required processing literally tons of pitchblende. The Curies processed approximately 10 tons of pitchblende residue over 4 years of work, the chemical processing conducted in the leaking shed, the boiling acid and the heavy lifting performed by Marie herself and by the workers they hired. The specific physical cost of 4 years of chemical processing at industrial scale conducted under conditions that modern health and safety regulations would have shut down immediately. They did not know that radium was killing them. The specific mechanism of radiation damage to biological tissue, the ionizing radiation breaking chemical bonds in DNA and cellular proteins, the specific cumulative damage that produces radiation sickness and cancer, was not understood in the 1890s. The Curies worked with their radioactive materials barehanded. Marie carried radioactive samples in her pockets. Their laboratory notebooks, so radioactive that they are still stored in lead-lined boxes and can only be examined with protective clothing, record the specific daily proximity to intense radiation that both of them maintained throughout their careers. Pierre died in 1906, killed by a horse-drawn cart in the street, not by radiation, in the specific cruel randomness of an accident that removed the most important scientific partner of his wife's life and that left her with 2 daughters and a research program to continue alone. The specific grief of Marie Curie after Pierre's death, documented in the private diary she kept for a year after the accident, addressed to Pierre directly as if he could still read it, is one of the most affecting documents in the history of science. She succeeded Pierre in his professorship at the Sorbonne, becoming the first woman to hold a professorship at France's most prestigious university, a fact she never emphasized and that her colleagues never quite allowed her to take for granted. The Nobel Prizes. Marie Curie is the only person in history to have won Nobel Prizes in two different scientific disciplines: the Physics Prize in 1903, shared with Pierre and with Becquerel for the discovery of radioactivity, and the Chemistry Prize in 1911, awarded solely to her for the discovery of radium and polonium and for the isolation of radium. The 1911 Nobel Prize was awarded in circumstances of extraordinary personal difficulty. The year before, the French press had published sensationalized reports of her relationship with the physicist Paul Langevin, a married man, a former student of Pierre's, in a campaign of character assassination that was simultaneously xenophobic and misogynistic, targeting her as a Polish foreigner and a woman who had transgressed the specific behavioral norms that the French establishment expected of a widow with children. The Swedish Academy, under pressure from some members who suggested she decline the prize given the scandal, received from her a letter of dignified precision that declined to accept any connection between her private life and her scientific achievements and indicated that she would attend the prize ceremony as she had planned. She attended. She received the prize. She gave the lecture. And then she collapsed. The specific combination of physical and emotional exhaustion of the most extraordinary 2 years in the life of the most decorated scientist of the 20th century, producing the physical breakdown that hospitalized her for the better part of a year. Ernest Rutherford, the New Zealand-born physicist who made the specific discoveries that transformed the understanding of radioactivity from a mysterious phenomenon into a comprehensible physical process, was working in Cambridge and then in Montreal and then in Manchester in the early years of the 20th century, conducting the systematic experimental investigation of radioactive emissions that eventually produced the nuclear model of the atom. His identification of the 3 types of radioactive emission, alpha rays, beta rays, and gamma rays, differing in their penetrating power and their behavior in magnetic fields, was the essential first step in understanding what radioactivity actually was. His discovery, with Frederick Soddy, that radioactive decay involved the transmutation of one element into another, that uranium decayed into a different element, that the radioactive decay chain was a sequence of elemental transformations, was the specific insight that demolished the classical assumption of the indestructibility and immutability of atoms. His gold foil experiment of 1909, in which he and Hans Geiger and Ernest Marston fired alpha particles at a thin gold foil and found that most passed through but a small fraction were deflected at large angles, was the experiment that revealed the nuclear structure of the atom. The specific large-angle deflections, which Rutherford famously described as being as surprising as if you fired artillery shells at tissue paper and they came back and hit you, implied the existence of a tiny, dense, positively charged nucleus at the center of the atom, surrounded by mostly empty space containing the electrons. The nuclear model of the atom replaced the plum pudding model of J.J. Thomson and established the specific physical picture of atomic structure that underlies all of modern physics and chemistry. The energy locked in the atomic nucleus, the specific equivalence of mass and energy that Einstein's special relativity had predicted in 1905 with the equation E=mc², was the most consequential implication of the nuclear model. The energy released in radioactive decay was nuclear energy, the specific binding energy of the nucleus being converted into the kinetic energy of the emitted particles and the gamma-ray photons. The vast magnitude of this energy, described by the specific constant c², the speed of light multiplied by itself, a number of approximately 9 times 10 to the power 16 joules per kilogram, implied that even tiny masses of nuclear material contained energy of extraordinary magnitude. The path from Becquerel's photographic plate to the Manhattan Project and the atomic bomb was not direct or inevitable. It required the theoretical physics of Einstein and Bohr and Heisenberg and Schrödinger. It required the experimental physics of Chadwick's 1932 discovery of the neutron. It required Enrico Fermi's 1934 discovery of neutron-induced nuclear reactions and his 1942 demonstration of the first controlled nuclear chain reaction beneath the stands of the University of Chicago's football stadium. It required the specific historical circumstances of World War II and the specific political decisions of the American government to produce the Manhattan Project and the specific terrible events of August 6 and August 9, 1945. The same physics that produced the atomic bomb produced nuclear power plants, which today provide approximately 10% of the world's electricity. The same physics produced radiotherapy for cancer, the specific use of radiation to kill tumor cells that is one of the most effective cancer treatments available. The same physics produced carbon-14 dating, the technique that uses the specific radioactive decay rate of the carbon-14 isotope to determine the age of organic materials up to approximately 50,000 years old, revolutionizing archaeology and geology and paleontology. The same physics produced nuclear medicine, the use of radioactive isotopes as tracers and imaging agents in medical diagnosis. Marie Curie died on July 4, 1934, of aplastic anemia, almost certainly caused by her decades of unprotected exposure to intense ionizing radiation. She was 66 years old. She had spent 40 years working with the radiation that killed her. She knew, in her final years, what radiation did to biological tissue. The science had advanced far enough that the mechanism of radiation damage was understood, and she appears to have accepted the specific cost of her life's work with the specific combination of clear-eyed acceptance and continued commitment that characterized everything she did. Her remains and pierres were transferred to the Pantheon in Paris in 1995, the mausoleum that houses the remains of France's greatest citizens. She became the first woman to be interred in the Pantheon on her own merits. The lead-lined boxes in the Bibliothèque Nationale de France that contain her notebooks will remain radioactive for approximately 1,500 years. The specific half-life of radium-226 is 1,600 years. She discovered it. It outlasted her. It will outlast everyone alive today. The invisible rays in Becquerel's drawer. The photographic plate exposed without sunlight in a Paris winter. The beginning of the story that changed matter from the fixed, immutable substance of classical physics into the dynamic, transformable, enormously energetic substance of the modern world. The atom had a nucleus. The nucleus had energy. The energy was real. And the woman who spent her life measuring it died of it. That is both the triumph and the tragedy of the most important discovery in the history of physics.